Good day again, everyone. My name is Adam Harris, Managing Director for C-Therm Technologies. Very pleased to welcome you to today's webinar presentation. Today's webinar presentation is an application highlight on the importance of negating the impact of convection in measuring accurately the thermal conductivity of liquids. I have with me Sarah Ackerman, the lead researcher with Thermal Analysis Labs, division of C-Therm Technologies. Unfortunately, Sarah has a little bit of a bout of laryngitis and is struggling a little bit in terms of public speaking as a result, but she will be weighing in on some of the application slide materials. I'm going to try to soldier on and cover the bulk of the background theory and provide a little bit of context to how we deal with convection with the MTPS method that C-Therm has developed, why it's such an appropriate method for testing liquids, and then I am going to pass it over to Sarah to highlight some of the application work that has been presented and published recently on the measurement of thermal conductivity of liquids. We may have to listen more carefully with Sarah, though, just in fair warning. She is having a little bit of issues with speaking today. So anyways, we will soldier on. Thank you again for joining us. We hope you find it of interest. The presentation should run approximately 45 minutes. Let's just jump into it. So first, maybe just a real quick little bit of background on C-Therm Technologies. We specialize in a very niche area of thermal analysis, and that's specifically in the non-destructive measurement of thermal conductivity via transient methods. And for that, we are the best in the world when it comes to measuring these types of thermal properties via transient methods. We've won numerous awards over the years, nationally and internationally, including here in Canada, the Shanghai Innovation Award. This is a really big deal here in our part of the world. Represented a $100,000 cash award to the original inventor of the technology. Internationally, it's also won us the R&D 100 award. Previous winners of the R&D 100 award, just to kind of give you a sense of the technical achievement and company that's put this in, would include developers of anti-lock brakes, the automated banking machine, smartphone, a number of very substantial technical innovations, and it certainly puts us in some good company. I'm just getting a note that there is a little bit of problem with the volume, so I will try to get closer to the speaker, but hopefully this works. So we're going to be talking about the measurement of thermal conductivity and specifically of liquids. I will just note that the platform measures a broad range of materials. So we're focused on liquids today, but there's a lot of use in testing batteries, tremendous amount of work in textiles, including incorporation of phase change materials with those types of textiles, nuclear, thermoelectric, materials of construction, explosives, traditional insulation of polymers and composites. So really the platform provides a significant capability for broad application. Just as a review, what is thermal conductivity? It is the rate at which heat flows through a material under a temperature gradient. The real important thing to remember about thermal conductivity is that it differs with each substance and depends on structure, density, humidity, pressure, temperature, powders, the packing density, or any kind of densification of the material, particle size distribution, crystallinity, morphology. All of these can have a significant influence over the effective thermal conductivity. And frankly, that's why it's so important to measure, so that you really do have representative data. Take good care and caution to measure under representative conditions. Probably one of the most common mistakes that I see made in this field related to thermal conductivity measurement is taking measurements under non-representative conditions. So sometimes that's a result of limitations or restrictions imposed by more traditional means of measuring thermal conductivity. But one of the significant benefits that's introduced with the MTPS platform that we're going to be talking about today is the ability to put these sensors that you see here on the upper right in all kinds of different operating environments. So you can really take them under representative conditions. Sometimes that means under radiated environments in hot boxes or in higher humidity environments and humidity chambers, elevated temperature conditions, elevated pressure. We have a range of high pressure cells for taking measurement of thermal conductivity at those types of conditions. So really it's important to understand that thermal conductivity will vary often with the material based on those conditions because it has a significant impact on the effective thermal conductivity of the material at that state. Today we're going to be talking mostly about the TCI thermal conductivity analyzer and how it's used with the MTPS sensor platform for measuring liquids. I will just put maybe just a real quick blurb in for our dilatometry product line. We have a very impressive range of dilatometers with capabilities up to 1600 degrees C. So one of the really nice things with this is it uses the same central electronics control platform. And what that allows is that you can really achieve some significant savings and economy with bundling those systems together. So typically it's in the range of about 35% in bundling the two systems together. The C-Therm TCI platform is available with a couple of different sensor options, but I'd say 80% are configured with the standard MTPS sensor. It offers the most versatility for testing liquids, powders, pastes, solids, conductive and insulative materials, really providing a broad range of performance. There is also available transient line source, or TLS. We call them needle probes. These are really good for dealing with very sticky situations, we'll call them. So it's a very robust sensor. It doesn't have quite the same sensitivity, but sometimes you will trade that off happily for a more robust interface. And so this is sheathed in stainless steel. Used a lot for testing polymer melts, for testing soils, sometimes different asphalt or bitumen material, and gives you a different option with the same package. So those are really nice complements to each other. And both methods meet a number of ASTM standards, respectively. In terms of the overall platform, you see a broad range of conductivity coverage, so we're just going to quickly hit on some of the specs so you can understand a little bit what it can do and what it can't do. It's important to understand both, of course, and considering any types of analytical methods. So this is really a solution that's appropriate for materials up to 500 watts per meter Kelvin. The temperature range for the standard sensor is -50 to 200 degrees C. There are some options to extend that up to 500 degrees C. The accuracy is better than 5%, and one of the things we're most proud of is the precision statement. It's an industry-leading better than 1%. There isn't a more precise means of measuring thermal conductivity commercially available. And as I mentioned in the previous slide, it conforms to a number of ASTM standards, including D7984, D5334, and D5930. We'd like to just highlight a little bit some of our client references. And if you go to our website, there's a really good page on client testimonials, and there's dozens of organizations listed and specific quotes from our clients. So you get a bit of a feel for what the client experience is like for a C-Therm client. This is the one that I like to highlight. It's, of course, a very interesting group that everybody is familiar with, NASA. And Dr. Enrique Jackson, our client there, comments that purchased a C-Therm TCI after seeing a demonstration of how fast and easy it is to operate. The instrument provides unequivocal results and provides the flexibility to test powders and liquids. So testing liquids was one of the key reasons they were focused on the C-Therm TCI. And he went on to say that he gave us a 10 out of 10 in satisfaction, so extremely satisfied. Just a note on the first part of that comment, the demonstration. This is something we certainly encourage. So if you are considering investment in this type of platform and are interested in seeing a demonstration of how it operates, that is something that we're quite pleased to offer. That can be done in a variety of formats. We do have folks all around the world, including our distribution network in 52 countries. But we can also do WebEx or Skype demos as well if it's a little bit more urgent and you'd like a quick understanding of what it looks like. We do offer an evaluation service, so if you wanted to provide 1 or 2 samples to have a look at what the data looks like on your actual materials, that's something we'd be pleased to explore with you further as well. So I'll just put a little bit of maybe a seed of thought there to revisit later. We measure directly 2 thermal properties with the TCI. We measure thermal conductivity. I'd say that's what 95% of our clients are using it for. We also measure another related thermal physical property called effusivity, sometimes called thermal inertia. It's the square root of the thermal conductivity, density, and heat capacity. There are a couple of reasons you might be interested in effusivity. I think it's a super interesting property as it relates to looking at touch qualification or touch experience. So in textiles, for example, it's used heavily to really quantify whether something feels warm or cool to the touch. That's a very important attribute for product performance in textiles. So today's webinar is not really addressing any of that. We're really focused on thermal conductivity. But if you are operating in other areas, including textiles or in consumer packaging, consumer goods, where touch experience is potentially important, then let me just kind of leave that there for us to revisit with you later. The other reason effusivity is sometimes interesting is because it does give you a pathway to determining heat capacity. So if you know the density of your material, you can see based on this equation, since we're obtaining thermal conductivity, and if you knew density, you could then derive heat capacity for the material. It's not going to be as accurate as measuring with a DSC in terms of determining the heat capacity, but sometimes with limited time, limited budget in a project, being able to generate additional thermophysical property data is of interest. So just something to consider. But focusing on thermal conductivity, let's talk a little bit more about how the sensor works. So the first thing to know is that this is a contact-based method for measuring thermal conductivity. So whatever the sample material is, whether that's a solid, liquid, powder, or paste, it has to come in active contact, intimate contact with the surface area of the sensor. Okay? We need to fully cover the active area of that sensor, which is approximately 18 millimeters in diameter. Okay? The measurement occurs by us applying current to the 2 circuits in the sensor. So there are 2 main elements to the sensor's design in terms of circuitry. There's the active sensor, which is the coil, and then there's also a guard ring which goes around the coil. So we apply current to both of these, and this provides a small amount of electrical heating in contact with the sample material. And at the same time, we are monitoring how that amount of energy causes a change in the temperature at the interface. That change in temperature over time at the interface is inversely proportional to the thermal conductivity of the material. We monitor the change in temperature by monitoring the voltage drop on the sensor. The voltage drop is calibrated to temperature change. So the easiest way to really relate to this measurement at a high level is to think of it as a measurement of temperature change over time. It's actually voltage over the square root of time, but it is effectively the slope change in that temperature change that we're using to determine and measure the thermal conductivity of the material. If we have a really good heat sink in contact with the sample material, it would be a more flatter rise in temperature. If we have a really good insulator material like foam, then there'll be a steeper change in the temperature over time. Important to note, it's an inverse relationship between those 2. I will just go back to this slide here just for a second and comment a little bit further on the guard ring. The guard ring is also heated, and the reason we do that is to ensure we get a one-dimensional heat flow into the sample material. That's very important from the perspective of the thermal properties we're looking to measure. So the sensor chip is mounted on a insulative backing material. We have heat being generated around the contour of the active sensor, and what this means is that where heat travels in the path of least resistance generally, we get a one-dimensional heat flow into the sample material. There are some caveats to this and conditions that are important to understand in relating to this. So we are typically using a very short test time, in the order of 1 to 3 seconds. For liquids, we keep that on the lower end of that scale at under 1 second. If you exaggerated the test time with this type of measurement, say you went for 30 seconds, you would certainly start to see some more significant lateral losses of heat, and some of these conditions would break down. But what's important to understand is that this is all provided pre-calibrated. The test methods are already set up for easily measuring a wide range of materials: polymers, ceramics, metals, liquids, insulation material, aerogels, all kinds of different materials. And what this does is it effectively really makes it easy to accurately generate thermal conductivity data that's very reproducible between different labs, between different users. This is simplifying thermal conductivity as much as possible. There isn't a simpler method to operate, and it's all based on the optimized sensor and pre-calibration of the sensor available for plug-and-play use in measuring thermal conductivity. So this next slide gives you a sense of what the software interface looks like. You get a tabular output of the thermal conductivity, the thermal effusivity, the temperature data. All of this is recorded in the database. It can also easily be exported to Excel. There's an automatic test generation function as well. If you want a more formal test report, it gives you remarkable capabilities in a very easy-to-use interface. Let's talk a little bit about the proof of the measurement and its performance. So when you're trying to really validate a new test method for measuring thermal conductivity or a new instrument, one of the best ways to do that is to go out and get a really good certified reference material. And if you look at the best sources of those materials, typically we would point to NIST in the U.S., the National Institute of Standards and Technology, or NPL, the National Physical Laboratory in the U.K. Both produce a limited availability of certified traceable reference materials for thermal conductivity. So in this case, we purchased some EPS. When you buy it, it comes with a certified value of 0.0337 watts per meter Kelvin. That's what represents this solid horizontal line here. But when you buy that, that certificate also says that it has an uncertainty to that value, and it's typically in the range of 2%. It's tested by guarded hot plate by our traditional ASTM methods. So that's what forms the uncertainty boundaries that you see listed here. So basically plus and minus 2%. And then these individual dots are the recorded measurements with the C-Therm MTPS sensor. So you can see it's actually testing on the edge of the uncertainty of the material itself. That certainly supports the accuracy statement of better than 5% accuracy, which would be basically out here, up to here, in terms of the range. So very good performance. Now this is just one example on EPS. Of course, just because you can perform on one material doesn't mean that your performance is the same across all material ranges and conditions. So there is a wide range of materials available, and in fact, one of the things we will do with providing a system is providing multiple reference materials. And that's different than most vendors. Most vendors will essentially pick one material and suggest that that's basically validating the full performance. We'll give you a range of different materials. Those materials include distilled water, if you want to test for liquids, pyrethrum, Pyrex, there's copper, phosphor bronze, a number of different materials available. Okay, so that's a very general introduction on the theory side of how the MTPS method works. We're going to kind of pivot more into the application in heat transfer fluids. So the first thing to really note, and this is right in the title of our presentation, is that one of the issues in measuring the conductivity of liquids is you've got this aspect of convection, another form of heat transfer. that you have to address, and you have to be cautious about ensuring that you have a means of recognizing that impact, so that if you're really trying to understand the conductivity of the material, you're not confusing that with the convection heat transfer occurring. Convection is the transfer of heat by the actual movement of the warmed matter. Is present in gas or liquid by movement of currents. It can also happen in some solids like sand, but really what we're dealing with here is more of the aspect of focusing in on the liquid. Conversely, conductivity is a transfer of energy through matter from particle to particle. There's a really great video on our YouTube channel where Dr. Jack Josephowitz explains conductivity and how it works from a physics perspective. It's worth checking out if you have, I think it's a 3-minute short little video tutorial on really detailing what's happening when we talk about conductivity, but it does a good job of really distinguishing how that works in terms of the mechanism from a physics perspective. For today's purposes, what we want to be careful of is distinguishing between the two and make sure that our test method is addressing it. So there are a couple of ways that we deal with convection in the measurement of liquids. And the lower the viscosity of the material, the greater the impact is in terms of the potential for convection. So there's a few things that we do from the onset that really help optimize this method for the measurement. The first is we reduce the volume requirements. So we have the smallest volume requirements for testing any fluid. I think it's, Sarah, about, what's the small volume test? 2 milliliters in volume. So it's a very small volume required for actually generating accurate test data on the material. The test time employed is 0.8 seconds, so it's a very short test in duration. The longer the test, the more opportunity there is for that material to move. And I'll highlight a little bit the implications of that in the next couple of slides. We also employ a very low energy, and this is of course also related to the test duration. The longer you're testing, the more energy you're putting into the sample itself. And so it's important to keep both of those in check. So essentially a short test time with a low energy power output is the optimal condition to negate the impact of convection. Just from an ease of use, this is the cell that is typically used. So this little cell sits on top of the standard sensor. It has an O-ring, a channel for the O-ring machined on the bottom side of it that you can't see. So it provides a liquid-tight seal, and you just pour the water into, or the liquid into the sample, and provides for a very easy mechanism for testing the material. This is some data that we had modeled in collaboration with the University of Moncton, where we did some evaluation on the impact of test time from a simulation perspective in dealing with aspects of convection. So the takeaway from this is that while the lines are nice and parallel, we have good conditions for understanding the conductivity of the material. But as we see, you start to see like a mushroom cloud formation develop as the test times become elongated. And this represents a sensor. It could be any sensor. It could be ours or other types of transient sensors in a liquid media such as water. So I think we used water as the material in this simulation. But you can really start to see how exaggerating those test times creates some significant issues in measuring and the impact of convection on it. So the longer that test time, the more energy we're putting into that sample, the more opportunity there is for convection. Now I'm going to share just some reference data with the MTPS sensor. So this is data on distilled water, thermal conductivity across the temperature range from 25 to 75 degrees C. So the measured values are the blue, and the reference values are the triangle. And you can see generally very good agreement there. with 5% error bars on that measurement. The next sample is an ethylene glycol, and similar performance over a bit of a wider temperature range. And then the last one is a transformer oil that we were measuring across a temperature range from -25 to 100 degrees C. So generally very good performance in agreement with some of the reference data for those materials. One of the more common applications for us in testing liquids is often from a process safety perspective, where one of the important conditions to represent is pressure. So we do have a special high pressure cell for testing liquids, testing up to 28 bar max pressure, up to 300 degrees Celsius. We'll replace the sealants for the higher temperature range with a Calres O-ring. This cell has been slightly redesigned since this picture was taken. Now the cell is mounted on the bottom, and that's one of those improvements that was made last year. And the reason and rationale for it was that what can happen is you'll get bubbles developing and start to bubble up and get stuck on the surface head of the sensor. So one of the changes that was made to the design of the cell is it was inverted. We just haven't got a chance to redo the pictures, but you get a sense of what it looks like as illustrated in these pictures. This is the cell inside the thermal chamber. I just give the interface here a chance to catch up. It seems to have frozen on me a little bit. There we go. So you can see some of the tubing in place. This is to equalize the pressure on the back side of the sensor, so it can accommodate a higher pressure condition. And then you have the sensor's cable in black there, wired to outside of the chamber. This is some data taken at elevated pressure conditions. Now this one's not terribly high pressure, but is at a higher temperature, so 14 psi-G, temperature is 300 degrees C. And this is a Duratherm heat transfer fluid tested across the temperature from 0 to 300 degrees C. So we can see a decreasing trend in the thermal conductivity of the fluid. So I think this next slide is a good point to maybe pass it over to Sarah. She's going to be highlighting some application data featuring use of the C-Therm TCI and testing different types of fluids with additives. So I think we'll be looking at a range of different additives, but this is a good slide just to kind of illustrate that really high conductivity of carbon nanotubes, diamond, and copper. Relative to other materials, we think of all metals as being relatively conductive thermally, but steel is only 14 to I think about 25 watts per meter Kelvin, depending on the grade. So compared to copper at 400 plus watts per meter Kelvin, or taken to another whole ballpark or extreme, carbon nanotubes at 3,000 watts per meter Kelvin. There's lots of really interesting novel work being done in these types of fluid systems focused on improving the thermal conductivity and heat dissipation capabilities of the material with the use of some of these types of additives. So without further ado, I will pass it over to Sarah. We may just have to listen more carefully. I'll get her as close to the mic as I can, but I know that she is really fighting with cold and laryngitis as a side effect. So anyways, we'll soldier on here.
Thank you, Adam, for the introduction. So, as Adam was saying earlier, this really kind of shows the relative thermal conductivity of some of the more common nanofluid and nanomaterial additives. Another one that's becoming a bit more popular lately is silver, and that's somewhere between copper and diamond at around 500 watts per meter Kelvin. So silver is going to show up in some of the later material that I'm going to present here. So moving into the application data, one of the works that I'd like to present is called Intriguingly High Thermal Conductivity Increment for Copper Oxide Nanowires contain nanofluids with low viscosity. This is work generated by the School of Environmental and Materials Engineering at Shanghai Polytechnic University, in collaboration with the Shanghai Innovation Institute for Materials. So this work was looking into copper oxide-based nanofluids. A bit more detail about copper oxide is that it's an appealing material to add to nanofluids because of its p-type semiconductor behavior, high thermal conductivity, low electrical conductivity, and its potential for catalytic activity, depending on the application that you're looking to use it for. The other basis for the work that they were doing was that a lot of research has suggested in recent years that nanofluid and nanocomposite additives with a high aspect ratio will tend to have a much higher thermal conductivity than additives, even with the same chemical composition, that have a lower aspect ratio at the same mass or volume loading. So if you're wanting to quantify that, what you would want to do is to characterize two different nanofluid additives that have the same chemical composition but different aspect ratios, and determine the effect of the aspect ratio on the thermal conductivity, which is what this work did. So this is just looking at the growth process of the nanowires that they were using, and they grew the nanowires thermally on a copper plate, and you can see some of the transmission electron microscopy images here and here of the nanowires that were grown. This work looked at two different types of additives. One has a very large aspect ratio, and that would be the nanowires we were talking about earlier. The other one has a very low aspect ratio, and that's copper oxide nanospheres, and they're almost completely symmetrical. They're not very interesting to look at, which is why I didn't include the TEM images in the webinar slides. But you can see the effect of the aspect ratio right away. These red dots down here are the copper oxide nanospheres, and in red here. Black is the same volume fraction loading with copper oxide nanowires, so that's the additive that has a very high aspect ratio. And compared with the neat fluid, the copper oxide nanowires are consistently able to achieve almost a 10-fold enhancement of the thermal conductivity as compared with the copper oxide nanospheres. So it just goes to show that the higher the aspect ratio of your nanofluid additive, the more thermal conductivity improvement you're going to see in the application. The last paper that we're going to look at is called Enhanced Thermal Conductivity for Nanofluids Containing Silver Nanowires with Different Shapes. So this was again exploring the effect of the shape factor of a nanofluid additive on the effective thermal conductivity of the nanofluid material. This work was done in partnership with the Shanghai Polytechnic University, Shanghai Innovation Institute for Materials, and also the Technical Institute of Physics and Chemistry at the Chinese Academy of Sciences. To prepare their nanofluids, they grew the nanofluid additives on a PVP polymer backbone, which allowed them to grow the silver nanowires according to different shapes. And they stirred it up basically, and then cooked off essentially the polymer material in an oil bath to get rid of that. And the different nanowires you can see here So the K88 nanowires, you can see, have this very kind of short and squat structure to them, so their aspect ratio is fairly low. And the K30 nanowires, by contrast, have a much larger aspect ratio, so you would expect for them to have more efficient improvement of the nanofluid thermal conductivity based on the research that we've seen previously. And that is in fact what we see here. So you can see at a volume percent loading of almost half a percent, the K30, which is the material with the higher aspect ratio, has almost has just about 4 times as much thermal conductivity enhancement relative to the K88 material. And in both cases, they're able to achieve a fairly sizable improvement in the thermal conductivity, particularly with the K30 material at very low volume fractions of loading, as low as 0.45%. So the takeaway from both of these papers, they both explore a common theme, is that the aspect ratio of your nanofluid additives is going to matter. And the higher the volume fraction, higher thermal conductivity, yes, but higher aspect ratio is going to give you a better bang for your buck in terms of the amount of nanofluid additive that you're going to be needing to use. So that basically sums up the application side of the talk for today. At this point, we'll be opening things up pretty soon, so I'll hand things back over to Adam to close out the rest of the talk.
Great. Thank you very much, Sarah. That said, just a couple of other items before we engage in the Q&A. So I mentioned earlier about the opportunity to do some sample testing or schedule a demonstration. So what I would encourage you to do, if that is something that is of interest, and there's no pressure to do that, it's simply an offer that if you would like us to help you take a look at some things and see if it makes sense for your group or for your particular type of materials, I would encourage you just to enter a short note in the chat box, just registering the request that you'd like either a demonstration scheduled or you'd like to submit some samples. We'll make a point of revisiting the chat box transcript and follow up with anyone on a one-to-one basis for that discussion. Lastly, I just will plug our website here a little bit. And the reason I do that is because there's a lot of technical resource and knowledge baked into this site. So all of these webinars, which are typically highlighting different user cases or applications of the C-Therm TCI's MTPS method, are recorded and available free of charge. There's a technical library which has an extensive listing of published works, presentations, different white papers on use of the technology. Of course, there's all the normal marketing stuff, brochures and videos, and there's a nice little blog there as well that Sarah often authors for us, just highlighting interesting and novel new things we're doing with different types of samples, typically oriented around highlighting a certain capability. So there's quite a bit there to explore if of interest. And with that said, let me close the formal part of our presentation just in saying thank you again. We very much appreciate the time. We know it's a busy time of year, a lot going on, and so very much appreciate you taking the opportunity to join us online for today's webinar presentation. And for those of you that will be dropping off, I wish you a good afternoon. And for anybody that would like to stay on and have some further discussion, please do so. But I will be stopping the recording here shortly. Thank you.